So I'm Patrick Cozy, CEO at Cesium, and I'm here to introduce Sean for the industry talk on Cesium. So separate from Cesium, I spent many years teaching GPU programming and architecture at the University of Pennsylvania. It was a graduate course, and according to the student ratings, I taught the hardest course in the department. But undergrads would take the course, and the undergrads were unbelievable. So one such undergrad when I taught in 2011 was Sean Lilley. He did a final project on order-independent translucency. And then thereafter, him and his brother and one other student did an independent study on sparse voxel octrees. This is back, 2011 or 2012. After graduation, he went to the Philadelphia Game Lab, and it took me a few years, but in 2015, he joined Cesium. He and I worked together very closely, writing a ton of code on the 3D tiles streaming engine that we'll talk about today, as well as designing the spatial data structures and the open standards for doing these massive models. And today, he is the real deal when it comes to our software architecture and our algorithms for 3D. And I'm mainly a mouthpiece, so I thought you should hear directly from Sean. So Sean, come on up.
All right. Hi, everyone. So yeah, my name is Sean Lilley. I'm going to be talking about 3D tiles. And really, 3D tiles is an open standard. We developed it for rendering massive models. And I kind of think of this talk as like a systems paper. So I'll be covering a lot of high-level topics, nothing in too much detail, but just kind of seeing how all these computer graphics concepts come together into production as 3D tiles. So before I get started, I just want to give a quick sort of intro for computer graphics in the Philly area. So, and this is also not an exhaustive list. So starting with Penn. Penn has an undergraduate, graduate, and PhD program specializing in computer graphics. Dr. Norm Badler joined Penn in 1974, and he established the computer graphics program and then led it for nearly 50 years. And you might have seen Norm yesterday at the happy hour. And many people at Cesium, Patrick included, me included, others included, were former students of this program. Also in West Philly is Drexel University, and the computer graphics program there started in 2003 with Dr. Dave Breen, who conducts level set research, and then Dr. Frank Lee and Dr. Paul Diefenbach, who founded Drexel's game design program, and that's a top 10 game design program in the US. And just recently in April, Rich Rabbits of Rowan University opened the Extended Reality Lab, where students build immersive experiences with AR, VR, and AI. And then at Bryn Mawr, Dr. Lynn Normile conducts research into digital humans and character animation, and Dr. Diana Shu does research in computational geometry. And then looking at some of the industry side, Bentley Systems, which is sort of just outside Philly, develops CAD software for infrastructure, and AGI develops modeling and simulation software for aerospace. And both were very early adopters of computer graphics, having some of the early SGI workstations. And Cesium itself actually spun out of AGI in 2019. And then on the outreach side, Create Access is a new organization that provides freely available courses for beginners, just to learn how to use different 3D creation tools and how to build virtual experiences, and hopefully eventually pursue careers in this field. And then as of last November, Philly now has its own SIGGRAPH chapter. So that kind of brings us to Cesium. So I mentioned that Cesium spun out of AGI, and that's kind of where our roots are, like in aerospace, like rendering the globe, rendering a large amount of objects, doing this in a time dynamic way, and also with high precision. And as we were building this, we kind of realized that this actually, like this technology applied to multiple industries. So it wasn't just aerospace, but the same concepts of like high level of detail and streaming applied to other industries. And at the same time, this also coincided with like an exponential growth of people who started to collect geospatial data from drones and eventually to like cell phones and other devices. So what does 3D geospatial data look like? It comes in many different forms. So on the top left, these are like the Cesium OpenStreetMap buildings data set that we have. We also have massive point clouds. We have massive textured meshes, usually produced from photogrammetry software. We have vector data like points, lines, and polygons that are draped on the globe, voxel data, instanced models, and then global terrain and imagery. Even though these all seem kind of different, they actually have several common themes. So the first one is that they're all georeferenced, and it's very important to have like accurate positioning of this data on the globe, because these are used in real world scenarios and simulations. It needs to be accurate. They're also massive scale. So we're talking like gigabytes to terabytes and also to petabytes of data that won't fit on a hard drive, won't fit in memory, and you kind of need streaming solutions in order to actually render this. Also, semantic metadata. So it's not just for visualization, but you also want to be able to carry through like attributes of the data that might be non-visual, such as like the point cloud classes, or if you have just annotations for your point clouds, or just any sort of semantic metadata. You want to be able to preserve that and carry that through. So once you have all this geospatial data, you have terabytes to petabytes of data. What do you actually want to do with it? So for a lot of people, they just want to be able to view it. Like they want to be able to bring it into a web browser or into a game engine and just look at it. That sometimes this is the first time they've looked at their data. And on top of that, they also want to be able to query it, to filter it, to style it based on the metadata that's embedded in the model. So all these use cases kind of came together, and then also our computer graphics backgrounds came together, and we took all these different concepts, and that's essentially how 3D tiles was formed, was from all these concepts and putting them all together. And it was, yeah, a combination of like the research side, but also like the practical side. Like as we were actually processing data sets ourselves, we started to notice common themes, and we just put it all together. So to give like a quick background of 3D tiles and what it is, 3D tiles is actually built on another open standard called GLTF. 3D tiles essentially provides the spatial subdivision. So it's like a tree structure. It provides links to the GLTF tiles and also provides georeferencing information. And then on the GLTF side, that's what provides the geometry and the textures and also the compression and the semantic metadata. And a lot of those are provided through GLTF extensions. So 3D tiles, really it is just like a bounding volume hierarchy. You have a few different bounding volume types, including boxes, geographic regions, and spheres. You also have a geometric error for every tile, and that basically determines when a tile refines to its children. You also have the content, which is usually GLTF content, and then each tile has children. And through the bounding volume hierarchy, you can build a wide variety of spatial data structures. So it's not limited to a specific type of data structure. Like if your data is suited for sort of a quad tree or oct tree, like a regular tiling approach, you can do that. If a KD tree is more appropriate, you could do that. And then also if you have data that sort of straddles tile boundaries, you can have tiles that slightly overlap, like sibling tiles that overlap. And overall, there aren't too many constraints. There are some, but in general, you're sort of free to pick whichever spatial data structure is best suited for the data that you're working with. And what the spatial data structure allows is sort of the concept I think we all know, which is like hierarchical level of detail, where you have, say, like a root tile that's a very simplified version of your model, and then it might have children that are like slightly more detailed, and then eventually you hit the leaf tiles, which are very highly detailed, if not the source resolution. And in order to know sort of when to switch from sort of the low detail to the high detail, you have this geometric error, which sort of says like how, like what is the error from the simplified version to the source version, and you encode that in the 3D tiles. And then geometric error is then converted to screen space error, so that at runtime you can use screen space error to determine when you have to load new tiles. So LOD selection, I put the absolute most basic example of what LOD selection might look like once you have 3D tiles. So this is a replacement refinement example based on screen space error. Essentially, you have a function that takes the camera state. You also take the tile's geometric error, and what you get back is a screen space error. And if the screen space error is less than or equal to the application-defined maximum screen space error, you select that tile. Otherwise, you recurse over the children, load those children, and potentially select those children. Of course, it gets a lot more complicated once you add any sorts of optimizations. So the first one, the sort of first obvious one would be culling. So frustum culling and other types of culling techniques add some complexity. one of the ones that adds probably the most complexity is being able to skip levels of detail, so that if your camera's looking at a particular location, you don't necessarily want to have the lowest detail tile load right away and then keep going progressively. You almost want the highest detail to be available as soon as possible, and you want to skip levels of detail. But the hard part is doing this while not having holes. And it's a very interesting problem and something that we're actively working on. You also can prioritize tile requests. So you could even potentially like understand where someone's looking and then prioritize those tiles over tiles that they might not be looking at. So sort of augment the screen space error that's already there. And then preloading. So if your camera is moving at a relatively fixed rate, or if you have a camera path and you know where the destination is, you can start to preload those tiles, and so that they're loaded by the time that you get there. And there's more optimizations, but there's a wide variety of things that can make this very simple snippet of code turn into a pretty complex code base. So kind of a quick survey of some of the culling techniques. So we use frustum culling in some of our runtimes. So we have Cesium Jest, Cesium for Unreal, Cesium for Unity, Cesium for Omniverse, and others. And in Unreal, we have occlusion culling. We're able to actually read back the results from Unreal. And then in some of our runtimes, we support fog culling, so just culling the tiles if they're basically going to be covered by fog entirely. And then probably the most geospatial of these would be horizon culling. So at a global scale, if you're kind of far away and you don't want to render tiles on the opposite side of the globe, so you should just skip those entirely. Another thing that's very specific to geospatial or really like massive models in general is precision issues. So the Earth is about 6 million meters radius, and that's the type of precision we have to deal with. And typically, if you're rendering this on 32-bit GPUs, it's just not enough. So this sort of manifests in a couple different ways. So first is like depth buffer precision. Typically, 32-bit is like 32-bit float is the most you're going to get, at least for typical devices. And for that, we have a few techniques. So we render the scene. Well, really, we combine two techniques, and this is for Cesium Jest. We render the scene in multiple frustums and then composite the result, essentially. And then within those frustums, we have a logarithmic depth buffer. And then there's also techniques like reverse Z and other things. So, but yeah, this does a pretty good job of at least the depth buffer precision side of things. And then for vertex precision, yeah, we do a couple of techniques here too. The most common one is relative to center rendering. So basically making sure vertex data is relative to as close as possible to 0 so that you avoid floating point precision issues. You're still eventually going to hit, like, if your mesh is big enough, you're still going to hit precision issues, but this is good for like tiles typically. And then for moving entities, we do like emulated double precision. So that's a different technique that works well for those types of things. On the compression side, this one's especially important for us. It makes a huge difference. Like, we want tiles to be basically small on disk. We want network transfer to be fast, and we also want to use as little GPU memory as possible. So these are extremely important for us. On the geometry side, there's really 3 techniques that we use. Quantization, which is sort of your basic, just quantized to like 16-bit. And then Draco and Mesh Opts are GLTF extensions that we take advantage of. They're also quantization based, but they have sort of domain specific compression on top of that. And yeah, they're both really good. And then texture compression, sort of your typical image formats like JPEG, PNG, and WebP. I think the most interesting one for us is KTX2 and Basis Universal. So this is basically a format that can transcode to GPU native formats. So you only have to encode it once, and it'll work on all sorts of devices. Like it'll transcode to the right format for iOS versus desktop versus Android. And this was a pretty big game changer as of the past couple of years. So just some results. I'm not going to read through the numbers here because it's a little bit hard to see and a little too much information, but the overall summary of this is like, we have this photogrammetry mesh data set. We applied Mesh Opt and KTX2 in this case, and what we saw was 82% smaller file size on disk, 81% less GPU memory usage. In particular, KTX helped a lot here. And then 48% 48% faster load time overall. So, I mean, if you scale this up to like global data sets that take up a ton of memory, like these compression matters a lot. And then, yeah, talking about the batching side, so how to just improve runtime performance. One thing we try to do is minimize draw calls. So we try to combine geometry and materials as much as we can. Sort of the simple but effective technique we use is to have a feature ID attribute, which is really just a vertex attribute that says what ID it is. And this enables you to actually like individually pick or style those features. And this is actually kind of one of the things that was, it's not necessarily a new concept, but in 3D tiles, it kind of blew people away a little bit, especially in the geospatial field, just seeing that you could like render all these models so efficiently. And it was a big deal for us. And then once you have the feature IDs, you can then use that to look up the metadata that you've also stored alongside your model. And then instancing. So we take advantage of GPU instancing. So for repeat geometry, this is, yeah, especially common for like data sets like this, where there's like a lot of repeated models, especially in like the AEC and CAD industry. It's very common to have repeated models. So this is a pretty good savings as well. And then on the metadata side, so this has been a pretty active area of focus for us recently. We've kind of separated it into 3 different parts. So there's a type system that we developed that provides the classes and the properties and also enums. And then there's the encodings. We have binary encodings. We have the ability to encode in a texture and also in JSON. It really depends on the granularity of your data as to which encoding you choose. And then above that, we have a semantic layer that provides semantic information to the types, and it could be like domain specific. So the AEC industry with formats such as IFC, for example, might have like their own domain specific semantics that you could encode in 3D tiles. And some of the examples I'm showing here, this is showing encoding per texel IDs on the mesh. So previously we had a lot of examples with like per vertex IDs, but more recently we've been doing per texel. So especially useful for like data sets that have been sort of classified from with AI ML algorithms. And the example on the bottom right is showing a per texel uncertainty value. So like the photogrammetry software that created this data set kind of knows how much error that individual section of the mesh has, and it gets encoded as a texture so that we can at runtime be able to like hover over it and see exactly the error amount there. So kind of in summary, 3D tiles is shaped by years of computer graphics research. There's a lot that's gone into it, and like on the topics of like compression, hierarchical level of detail, streaming algorithms, it's all kind of coming together in 3D tiles. And then 3D tiles is designed for rendering semantically rich massive models. And it's not just geospatial, even though that's a lot of our examples. It's really designed for any sorts of massive models that need hierarchical level of detail and need a streaming solution. And then, yeah, so far we've had pretty good industry adoption, and a lot of that is through using open standards. So 3D tiles itself being an open standard, and then being built on GLTF, which is an open standard. We've been able to leverage just everything the community has built, all the awesome GLTF extensions that are out there. And it's really been a good choice, basically, to go open in this case. So some of the areas of interest for us on the research front. So I maybe touched on this a little, but we're interested in use case specific traversal algorithms. So you might not want to use a generic algorithm if you want to optimize for like VR, or maybe maybe you have like a specific algorithm that's better for interiors than exteriors. So we want to explore this area some more. And then something that's been also talked a lot during this conference is Gaussian splatting. And we've done a lot with point cloud rendering, but we'd also like to leverage whatever the GLTF community builds for Gaussian splats and sort of be able to render those as well in our runtimes. And then also time dynamic data and ND data is especially interesting to us for voxels in particular. We have a lot of data sets that are massive data sets that vary in time, and we want to be able to render that efficiently. and then editing as well. So even though 3D tiles is kind of designed to be a runtime format, there are a lot of use cases for being able to edit things, especially to edit the metadata. And we're just continuing to think about like workflows for improving editing for 3D tiles. So that's it for my presentation, and I'm happy to take any questions.
Thanks for the talk. This is really cool. I was curious about your how you handle adjacent different LODs. Like, do you do anything special to kind of prevent cracks or anything, or you just kind of live with it, try to stream in the one that matches its neighbor, or like what do you do?
Yeah. So the most basic technique we use is to have what we call like terrain skirts. So just drape some geometry, and then generally you don't notice the skirts you don't notice the cracks when you have those. I think in the past we've also explored like GPU-based techniques to try to fill in the gaps. But yeah, it's still an area of interest and research for us.
Hi, question. So I find that, like building large 3D applications, like whenever you scale, a new bottleneck shows up, and then you find a way around that, and then you scale again, and a new bottleneck shows up. So I'm wondering if you can share what your current bottlenecks are. Do they exist? And what do you need from the industry to solve them?
Yeah, that's a good question. I think at least one bottleneck on maybe the semantic metadata side is once you've tiled data, you still need to reference, or you still have multiple data or multiple objects in the data set that are referencing the same metadata database. And how do you do that efficiently? That's maybe one example. And then, I mean, so far we haven't had too much, I guess, scalability issues with 3D tiles itself. Maybe if you're, yeah, I'll have to think about that some more. Yeah.
Sean, thanks for the presentation. So the question I have might not be related to your presentation specifically, but since you're smart, I'm going to ask it anyway, because there's a problem that I'm trying to address, and I have sort of run into a wall. As a game designer, what I'm trying to, I had a large grant to try to recreate World of Worlds as a citywide augmented reality experience. So in my mind, what I had in mind was through, let's say, Center City, right? Maybe 4 or 5 blocks down the line, there's a huge robot looking through your phone, sort of coming in, blasting things away. So looking at your accurate model of the city of Philadelphia, the solution that we tried to get to was read in essentially open city data to recreate the locations of the building and try to match that, align that with the real data coming from the video feed. But that was a problem. The other thing was, when I was really excited about AR and its potential use in play, but AR at this point is really related to very local, small areas using kind of LiDAR that's available to try to do 3D mappings of sort of small spaces. Is there anything that your experience using geospatial data and your experience doing this that might help me to try to create that type of an experience at a large scale?
Yeah, I think getting the georeferencing right for all the different input data sets, I think, is probably one of the more important things. Getting like the camera pose from the device would be another. Yeah, and then I guess making sure that everything is rendered at high precision would be important as well. Yeah.
Thanks very much.
Oh, I have a question. Looking at the monitors, we see all these very cool models, and there's some that like there's airplane flying. So I guess sometimes you mix different kind of models in the same rendering, right?
Yeah.
And then you said you can use many different spatial data structures, but some are more adapted, like points, the other from meshes and things like this. Do you also like mix these data structures when you have like this different kind of models, or you keep only one? Because I think mixing them is always kind of a challenge also.
Yeah, so you could do that. So 3D tiles, you could have like a different spatial data structure like higher up in the tree. And then once you hit content that might benefit from a different spatial data structure, you could sort of switch to that. And you could do that through a few different ways. But yeah, I think, yeah, different data sets can be incorporated into the same 3D tiles data set and employ different spatial data structures within the same 3D tile set.
Are there any more questions? Yes.
Sorry. This may be a dumb question. So how this 3D tiles compare to say UE5? And since they claim, they also claim they can handle large models, large terrains, and they are using some LD techniques that are suited for movie production needs, blah blah blah. So what was the situation here?
Yeah, so nanite I think would be the main example there. Yeah. So well, I guess one major difference right now, at least, is that nanite is sort of baked at editor time, whereas 3D tiles can be streamed sort of dynamically. So that's one of the big differences. But actually, we're pretty inspired by nanite, and I wouldn't count it out to have nanite-like techniques in 3D tiles eventually. But it's still, I mean, it's super early for that. But
thank you. And my second question is it's about the selection of the file format. You mentioned that you use the GLTF. Well, I've heard that from a media they use USD, Universal Scene Description, and can you tell your thoughts on it on this matter?
Yeah, so I think the major difference is that GLTF is built for runtime efficiency, whereas USD is built for composition and sort of building scenes more at editor time.
Okay.
And there are like interops between USD and GLTF, but in general, I think they have sort of different use cases.
Okay, thank you.
Okay, one more question.
So very quick. I mean, I'm just wondering, what are the criteria you follow to load or preload the next expected 3D tile?
Oh yeah, so for like the preloading side, yeah. So one thing is you could try to basically use camera information or predicted camera information to know where the camera's going to look, and then you can sort of run your selection algorithm on that state and fetch the tiles in advance. There's a few different techniques that we've tried out, but
I see. Like 15 years ago, I worked on a similar problem for a helicopter simulator. So, and I had to load whole UK map and then decide, but we decide to load the next tile when the size of the pixel in the pixel, the bounding volume in the pixel size of the screen will be already maybe 1 or 2 pixels, and then blend with the current, so to make a smooth transition from tile to tile.
Yeah, so that's what we do too. Like we do it based on screen space error, and in some engines we do blending as well.
All right, so thanks Sean again.
Thank you.
Very nice talk.